Hello everyone, and welcome back to the channel. Today, we're talking about one of the most important pieces of digital logic, adders. These are the circuits that let computers add numbers together, and, with a little extra wiring, they can handle tons of other operations as well. Adders are the foundation of the ALU, the part of the CPU that handles your math and logic. Even things like calculating bullet trajectories in Rust, that's just algorithms being crunched by an ALU or GPU under the hood. Let's start with the building block of every ALU, the half adder. A half adder takes two input bits, A and B, and gives you two outputs, the sum, which is the direct result of adding those bits, and the carry, which only appears when both inputs are 1. Binary addition for a single bit works like this. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. And 1 plus 1 equals 0 with a carry of 1. Just like in decimal, when you carry over to the tens place. So the half adder tells you two things. What the sum bit should be, and whether adding those inputs overflowed into the next binary position. A half adder can be built using two basic logic gates. An XOR gate for the sum, and an AND gate for the carry. A half adder is great, but it only lets us add two bits by themselves. In real designs, we're almost always adding multi-bit numbers. That means each bit needs to know whether the previous bit produced a carry. So we need a circuit that can add 3 bits, A, B, and a carry in. That's where the full adder comes in.
The full adder, tiny in silicon, but a heavyweight in logic.
A full adder is traditionally built using two half adders and an OR gate. The first half adder adds A and B, giving you an intermediate sum and carry. And the second half adder takes the intermediate sum and adds the carry in. That gives you the final sum and output. Meanwhile, the OR gate combines the two carry signals. If either half adder produced a carry, the final carry out becomes 1. Now that we have a circuit that accepts the carry in, we can start chaining them together. If you want a 4-bit adder, you line up 4 full adders in a row. The carry out of the least significant bit goes into the next adder's carry in, and the ripple continues all the way up. Because the carry ripples from one stage to the next, this design is called a ripple carry adder. It's simple, reliable, and is the foundation of most beginner ALU and CPU designs. The full adder is the heart of addition, but with a bit of extra wiring, some control signals. The same chain of adders can do a whole lot more. You can perform subtraction, incrementing, de-incrementing, bitwise logic like AND, OR, or XOR, and even comparisons. That's why the full adder shows up everywhere in digital logic. Now here's something I want to point out. When most people look up a full adder online, they see the exact same diagram every time. 2 half adders and an OR gate. That's the classic version, but it's not the only way to build one. There are tons of different designs out there, including some that use what's called threshold style behavior, where a weighted combination of the inputs triggers the output. And actually, The full adder I built for this project is a good example. It doesn't follow the textbook layout, and it doesn't look like the standard diagram you've seen 100 times. But it still produces the correct sum and carry for every input combination. And that's what matters. That's the big takeaway here. Logic design isn't about copying the exact structure someone else used. It's about understanding the behavior you want and creating a circuit that produces it. You can think outside the box, you can try different wiring setups, and you can experiment with the parts you have available. If the output matches the truth table, then congratulations, you've built a valid full adder. And that's honestly one of the coolest things about digital logic. There's the standard way to build something, and then there are all the creative ways you can discover on your own. So get out there and start wiring.